Hi, my name is Natalie Lorenz Anderson, MIT class of '84, and I'm pleased to talk with you today about a real business problem that we're trying to solve, and that is to leverage AI to help us identify a 10-day cloud cover and solar radiation forecast that will optimize solar energy production not only for concentrated solar power system that we're developing, but also for photovoltaics and really any other system that uses either photovoltaics or mirrors. Our team included myself and Emmanual Abimbola Adebayo from Nigeria, working across many time zones together. I like this photo of my son and my mom because it shows that I feel like the little guy, not able to reach the basket with my AI skills, and my mom playing the technical assist role that we've had from several other participants in the program, and also the mentors from AFES and Stack AI. The problem that we're trying to solve is that the sun doesn't always shine, and traditional solar, photovoltaic or concentrated solar power systems need alternative ways to operate, but they need to have a heads up because we need to be able to switch to thermal storage, electrical storage, or some other storage mechanism when the cloud cover is going to arrive. And we also need to be able to do this in a seamless way, or switch to backup power, such as natural gas or other power sources that may be integrated into the system. Our solution that we had in mind when we started this course was to be able to leverage artificial intelligence and generative AI for us to be able to take real-time solar radiation and cloud cover data from models that are already out there that are very good. Solcast, GenCast, and many others are available to us. We felt that we could take that to predict when the cloud cover would arrive. Within even 15 minutes is helpful, but especially if you know hours or a couple of days ahead of time, because then you can be sure that your control system is programmed to deal with the fact that you're going to have a drop or a change in the production of the energy level and be able to switch to the battery, thermal storage, or other alternative energy production mechanism in a timely manner without missing a beat and without affecting the customer. For this particular class, we tried just to take on the forecasting aspect and tried to integrate national radar cloud cover data. We tried to integrate Solcast API with the Stack AI engine as the main engine, and then the large language model being, at this point, ChatGPT 4.0. You can see here some of the code that would have been generated if we understood how to use Python correctly. So the ChatGPT gave us this option as a way to deal with creating the code, but no matter what we've tried, we've not been able to get the code to work. So this shows us what the model was supposed to look like, where you have an input of latitude and longitude, number of hours, and then you would use the API, Solcast or GenCast or some other, to basically ask it to give you the next 10 days on an hourly basis while the sun is shining, what that answer would be with regarding to cloud cover and what we call solar radiation. So from a risk management standpoint, our primary focus is during this class has been on looking at the beta aspects of this. The overall project is bigger than this, but we wanted to leverage AI to give us this kind of data. So there are three areas of risk. The excessive energy use associated with using an AI model and running that model repeatedly. We feel that while the prediction tools are already available, integration with our model requires real programming talent that we don't have yet. But also we'd like to be able to design and model this so that we reduce the energy cost of AI run cycles. So in the longer term, we would monitor those costs, and then we would mitigate by refining the models to improve the efficiency of the runs. We're also looking at accuracy and availability of data from these sources. The incoming administration focus on closing down public sources of climate data is a big concern for us. So we would absolutely need to pay for and rely on private and costly models The issue associated with that is that those models could be inaccurate. They might themselves not be, they might be relying on public data as well and might not be available to us longer term. So our approach would have to be to assess the viability of these models, to monitor and to mitigate the shortcomings from these data sources. And then finally, the bigger picture is to integrate what we learn from this project with our overall system architecture. We have a control system. In our case, we are controlling the mirrors to align with where the sun is at any given time of day in the correct azimuth and horizontal coverage. And what we're trying to do is anticipate cloud cover and other situations that would cause us to have to activate our storage system or alternative sources of energy. But we also think that photovoltaics would benefit from this kind of an approach. Longer term, we need to assess the impact during our testing and our first commercial plant integration of putting this all together, monitoring its performance, and then mitigating it through subsequent design and build cycles. Finally, the next steps for us, we have a long way to go, but we'd like to learn how to successfully leverage these APIs from these proprietary tools, which means we need to learn how to do that, perhaps not using Stack AI, so we're going to be embarking on that. We want to work with the folks that are developing the mirror control system and the storage and backup power system software so that we can integrate this subset of code into the control system code. Then we need to test this, build it into our first commercial plant, which is going to be built this year, gather any relevant data and results, and then feed that back into our models. And then if we find it's useful, we would like to consider offering the software that is developed here to the market if it's truly unique. And at that point, we would do a market assessment to figure out the total addressable market and how to price this and, all of that goes into a successful software development project. Thank you so much. It's been a fun project and we look forward to more.